Hello everyone. My name is Delafrouz Mirfendereski, and today I'll be presenting our research under supervision of Professor Barbara Chapman. Our research is about resilience methods for HPC parallel programming models, especially our own implementation of a checkpoint restore library for OpenSHMEM, which is a PGAS parallel programming model. The research currently shows that on some supercomputers, failures are happening almost once or twice a day. And scientists expect that when these supercomputers grow in size, then the rate of errors would also go higher, because imagine that if on a supercomputer nodes are failing every 10 hours, then if the supercomputer grows 100 times in size, then the error rate would go to 1/10 of an hour, which is 6 minutes. So it is expected that when we move to exascale sized machines, the error rate will drop to every few minutes. So although we might be able to reach exascale machines, but applications won't be able to benefit from this performance, which would cause a delay in reaching exascale error and exascale performance, and also cause high costs of energy consumption in time and other resources. So a lot of researchers are focusing on resilience methods for high performance computing. And there are a lot of things to study here. We can study costs of failures, their types, and how often they happen. And we can also study decisions and actions we can take, and even if we want to take action. So for example, there are many preventive methods, many predictive methods, and decisions about how we should detect if failures have happened, what should we do, how to propagate this information to other parts of a system that have gone through the failure, and also if we want to have a recovery plan or a repair plan. Here I am quickly introducing some techniques that are related to our own research. There are two very famous resilience techniques. One is redundancy, and the other is recovery. So in redundancy, which itself has two categories, data redundancy or computation redundancy. In computation redundancy, we are having 3 or more versions of a program running in parallel on different processes. And at the end, we're checking the results of these programs either by a voting system or a self-checking system. So for example, voting system, if 2 out of 3 processes have reached the same result, then we will assume that that result is the correct one. In data redundancy, we are making copies and saving these copies of different states or data made by computed by the program. In recovery method, the basic thing is to try to escape from the state that has failed. We either try to move forward or move backward, which means that in forward recovery, we're skipping to a safe state in the future. But in backward recovery, we are going back into the last safe state that we have saved. These two are differently used based on the system we have. For example, forward recovery is mostly used in systems that are real time, and performance is more important than the result. However, backward recovery is used in systems that accuracy and the result is more important than when we are reaching the result. These two are the mostly used techniques for resilience, and usually backward recovery is used together with data redundancy, because we have to have a saved state to go back to. And this method is also called checkpoint restart, or CR for short, and it's probably the most used HPC fault tolerance method here. I'll briefly introduce OpenSHMEM. OpenSHMEM is a PGAS, partition global address space, a parallel programming model. It follows this PMD, meaning the programmer can write a single program and run it on parallel processes on different data. Its API provides many functionalities for users, such as memory management, communication between processes, remote memory access, atomics, mutual exclusion, and many other functionalities that are common between parallel programming models. One very important feature of OpenSHMEM is that the memory of processes in OpenSHMEM, which we call processes here PEs, which is short for processing elements. So the memory of processes in OpenSHMEM consists of two subparts. One part is the private memory, which holds the private variables. The other is symmetric memory, which itself consists of two other parts: global and static variables, as well as symmetric heap. This symmetric portion of memory is one that is accessible by all other processes. So, for example, all these other processes can access PE0's symmetric memory. This symmetric memory is how OpenSHMEM has implemented communications. So as most of you might be more familiar with MPI, I'll just mention some similarities and differences between these two. Their similarities is that they're both formal specifications designed by standard organizations. Their main difference is, however, in their way of communication. And although both of them support one-sided communication, MPI was built from the beginning based on two-sided type of communication, but OpenSHMEM from the beginning was built upon one-sided communication idea, and also their own their implementations of this one-sided communication is different. As I mentioned, OpenSHMEM does this using the symmetric memory. However, it's done using windows in MPI. There are some works regarding resilience for HPC parallel programming models. Some libraries out there have they inherently have resilience techniques inside them. Some examples are GASP and GVR. So in GASP, all the blocking functions have a timeout, so no operation blocks indefinitely. And in GVR, multiple versions and copies of the data is saved, so they can use them in future if a failure happens. But other libraries such as MPI and OpenSHMEM, they're not inherently built resilient, so they have to use the support of other fault tolerance libraries. Some of these are, for example, user level failure mitigation, or ULFM for MPI, which categorizes the errors that can happen in an MPI application, and it can also help with when processes fail in an MPI application. So they can respawn new processes, and they can also ULFM can also help with reconstructing communicators that have had failed processes in themselves. There are also many checkpoint restart libraries that are either built for MPI or can be used for MPI applications. Some of these examples are fault tolerance interface and scalable checkpoint and restart. Both of them are multi-level checkpoint restart libraries. Some other examples are Velocity, Phoenix, and Craft. some of these leverage ULFM to handle failures in processes. One thing that is common between many of these application-based checkpoint restart libraries is that they need the user to request for reservation of memory before they start to checkpoint their data. So they have to ask for some place in the memory for the data they will later checkpoint. The only work we know in for resilience in OpenSHMEM is this work that is a checkpoint restart library for OpenSHMEM. And what it does is that in two different modes, they provide one or two copies of the whole symmetric heap. So in single backup mode, they save one copy of the symmetric heap inside a neighboring process. And in dual backup mode, they other than this remote copy, they also save one local copy of the symmetric memory inside the process itself. So this local copy helps when we are trying to restart the program and go back to the last checkpoint, because this local copy can be just reloaded from a PE's own memory, and they don't need to communicate with other PEs to get information. They will just go back to their own memory. So the model we have designed for checkpoint restart for OpenSHMEM has had inspirations from all of these work that I just mentioned. Our model is an application-based in-memory checkpoint, and we use pre-spawn PEs. So at the beginning of the checkpoint restart zone, we set aside some of the processes as spares, and later we use them as places that checkpoints are being saved. And if other processes fail, these spare PEs can just replace them and reload the data. We provide two levels of checkpoints. One level is local to the process itself, and the other, at least two copies, are also kept inside partners, inside some neighbors, other processes. As I mentioned, this local copy helps us boost the performance of restarts, or as we call rollbacks. We also try to always have at least two remote copies of checkpoints. It will help us when some of those copies are lost, so we have at least another one most of the time. And we also allow the user to checkpoint whatever piece of memory they need. They can checkpoint data from the private memory as well as the symmetric memory. But whenever a failure happens, we do a global restart, which means that all processes will have to go back to the last checkpoint. All of them will roll back. We also ask the user to reserve a memory, to ask for reservation of memory before they start checkpointing. As I mentioned at the beginning of program, we set aside some processes as spares. So there are different types of processes. One is active processes, which will actively run the main program. The other ones are spare processes, which themselves have two types. They're either storage processes or dormant processes. We have implemented two modes. So in one mode, all of the spare processes act as storages. But in another one, some of them just stay dormant, and the others keep the checkpoints in themselves. So when one of the active processes fail, a storage PE will just reload their last checkpoint of this active PE and will replace them and continue running the program from that moment. And if you have any dormant PEs, then when the failures has happened, one of the dormant PEs will also replace the storage PE that replaced the active PE here. So we'll make sure that this way our numbers of copies remains the same. So as I mentioned, we implemented two modes, two copy mode and many copy mode. In many copy mode, this is the mode that all spare processes keep copies in themselves. And I also mentioned that we keep one local copy of checkpoints inside the PE's own memory. And we call this shadow memory. I'll just go through some details in our implementation. All of these are, of course, invisible to the user. This is just how we have implemented this. So these are a diagram for active processes. Active processes have two parts of their memory, just as any other process, private memory and symmetric memory. They have one copy of the checkpoints kept in themselves, and they can keep checkpoints of private memory, or for example, this I is from private memory, or they can keep checkpoints of data in their symmetric memory. For example, this are here. But as I mentioned, in OpenSHMEM, only communications can only happen from symmetric memories. This is why for requesting reservations and checkpoint, we have these two data types, which we'll call carriers here. Both of these reside inside this symmetric memory of an active process. And what these two do is that they just keep information about the reservation request or the checkpoint request in themselves, and they will just carry the information from an active process to a storage process, which I'll show in here. The carriers that those active messages send will be kept into different queues here. One queue is for reservation requests, and the other is for checkpoint requests. And every storage PE will have one of two of these queues, one for reservation and one for checkpoint. And every storage PE will go one by one through these requests, and just based on the kind of request, they will act accordingly. And one storage PE holds the checkpoint of all active PEs. So for example, in this row, they're holding the checkpoints of PE process 0 or process 1 here, and so on. So we have run our implementation. We have tested it with a matrix multiplication application on Stony Brook Seawolf cluster. I haven't brought the specification of the cluster here, but if anyone's interested, I can provide more info. Just to lengthen our program, we have run this matrix multiplication in 200,000 iterations, and we have inserted checkpoints every 400 or every 1,000 iteration. Our results show that the checkpointing itself have very low overhead in execution time. So for example, when in many copy mode, when all of the spare processes keep their checkpoints, we have up to 5.5% increase in execution time. In two copy mode, we only have 3% overhead in execution time. What we saw was that in this example, we had a significant overhead for initialization of the program. That is when PEs are separated in types, and we start allocating memory on them for storages, for shadow memory and storages. But the thing is that if this initialization only happens once, so if the execution time of the program was much larger than this initialization overhead would just stay the same as this program. So this is the difference of performance in many copy mode and two copy mode. As we could see, when we are only keeping two copies of the program, the performance is better than when keeping multiple copies. The only difference is that we expect, as we expect, in many copy mode, the performance is better when we are trying to restart the processes, and that is because when we only hold 2 copies, if a process fails, then a storage PE will replace it, and then we have to make another copy. So the rollback in 2 copy mode will have more overhead than many copy mode. This is also the result of when we have restarted the program for once or twice. And we could see that our program has, our implementation has up to 4% more overhead in execution time when we have 1 or 2 rollbacks in the program. This means that 1 rollback means that 1 process failed, and 2 rollbacks means that 2 processes failed. So in summary, we have studied resilience techniques, and we have implemented a checkpoint restart library for OpenSHMEM, which provides multi-level checkpointing and multiple copies of the data the programmer wants to save. And we have seen that it has very low checkpoint and rollback overhead. But this is obviously a starting point in resilience work for OpenSHMEM. So there are a lot of paths we can follow for future work. We are seeing into different kinds of implementations into copy mode, because we're trying to lower the memory overhead by distributing the checkpoints in a round-robin model instead of just one storage peak keeping all of the checkpoints. We're also looking into file support, IO support, meaning that we keep copies in files as well. We're also investigating compiler contribution and how it can support our library and enable the programmer and make suggestions probably on how they can maybe where in the program they need to insert checkpoints, because like their data is being changed a lot. So thank you everyone for listening. I also wanted to thank the conference executors for providing this opportunity for us. This was a unique chance for me. This was a unique experience for me to attend an online conference like this. So thank you. If you have any questions, I'll be taking them. Thanks.
Thank you very much. We have a first question. Thank you, Delafrouz. Very interesting talk. And now a question from Carol. Delafrouz, can you see the chat?
Yes, yeah. So they're asking what's the memory overhead of this checkpoint. So as you can see, we're keeping multiple copies of checkpoints. We either keep 2 copies or multiple copies. So this is based, and also, as I mentioned at the beginning of the program, we're setting aside some spare PEs. That number of spare PEs is completely up to the user themselves. So imagine they can say, I need 4 spare PEs or I need 8 spare PEs. That is completely up to them. And in many copy mode, they can use all of those spare PEs as storages. So we cannot completely come up with one overhead for memory. It's up to as many copies as we have. And also it's up to the user to, because maybe they only need to checkpoint one single integer, for example, or they need to checkpoint everything they're calculating. And so it varies a lot from like keeping only a few integers or like the whole memory and keeping either 2 copies or much more copies. That's not one single answer to that.
Okay. Well, I'll allow myself again to tie in what you were talking about to two or three talks, previous talks that we've heard over the last 2 or 3 days. This checkpointing to people who are on the application side, scientists. They sometimes don't realize how costly it is to fail. Failure in computation that you started with extremely costly. And I can give you a back of the envelope estimate. If let's say typical larger supercomputer in the US costs $250 million, and it's supposed to run for 5 years, so it's about $50 million per year. The cost of running one application a day is upwards of $100,000, sometimes up to $300,000 if you include cost of storage. And then you had, so that's something that Łukasz Orłowski mentioned. He said tens of $1,000s per day for calculations. It's actually one order of magnitude more, perhaps. And then several people presented the molecular dynamics simulations, and the holy grail of molecular dynamics are this long trajectory, long time calculations of millisecond. That's where
Exactly.
you observe interesting chemical, biological phenomena, things happening. So in order to run it on current day supercomputers, you need days, okay, many. In some smaller situations, I observed when a program ran for days and days. And then imagine now that the program like that crashes without checkpointing. How much money you lose on that. So it's not only your time is wasted, you have to sort of, if you didn't have checkpointing, that's a disaster. So checkpoint is absolutely critical.
Yes,
And
exactly. And also it's that some programs are very critical. So for example, weather forecast programs.
right,
And if they lose their data, they'll won't be able to maybe forecast disasters, which will cost millions or billions even of dollars. So
right,
imagine if they couldn't predict a flood or a storm, that would also cost a
right,
lot.
right. And yet another thing that ties into what our Warsaw team, student competition, team that competes in the student competition. One of the problems that now frequently appears at SC competition is restarting, checkpoint and restarting. So now student teams are actually, that's one of the problems they have to compete at. That suddenly all the teams lose power to their computers. They basically deliberately crash the certain part of the computer, and they have to restart it. So of course that's now part of a competition. So now, do we have any other questions from the audience? Well, it looks like that's. Oh yes, there is. Angel.
Are the checkpoints described included in the stable release of OpenSHMEM? Right now, no. This is just an addition to OpenSHMEM. It's a separate library that can be added to OpenSHMEM. But this is also something that we're looking to in future, that maybe we can use this kind of resilience support inherent to OpenSHMEM, so the user can just use them when they're using OpenSHMEM.
Okay, maybe my last question. How far is your work from being sort of a ready product? It's clearly the description of work in progress.
Yes. This was part of a 3-year project, and obviously we are also looking into different things such as compiler contribution, as I mentioned. So what you're trying to do is quickly make this available for OpenSHMEM.
Right.
Yeah.
Okay, Delafrouz, thank you very much.
Thank you.